Again, I'm Stephanie Woodman. I'm coming from Yale University at the Laboratory, and today I wanted to present my work on stretchable shape sensing ribbons. And so first, I wanted to start off with the vision of not only the future of this work, but the future of my PhD, and that is shape-changing robots. And we're defining this as a robot that changes its resting shape or unactuated shape to adapt to new environments. And so, for example, in this lovely illustration, you have some spherical robot that stretches, strains to become this inchworm type robot, and then maybe stretches even more to become a quadruped, grow legs, and that kind of thing. And so what's necessary for shape change is the surface strains. The material necessarily stretches, and that makes soft robots a promising candidate for future shape-changing robots. And so if you haven't heard of soft robotics, that's my primary field. This is the canonical first soft robot that is a quadruped, and so it has a bunch of pressure regulators and it's pneumatically actuated to inflate and walk in this quadruped type motion. And this is really nice because this elastomer material that it's made out of can stretch to 1000% strain before breaking, making extreme shape change possible. And so to date, there have been a couple of really wonderful examples of shape-changing robots in the field. The first one is this turtle robot that was developed in our lab. And it can go from a tortoise-inspired walking gait to swimming by morphing its leg shape. And so it uses pneumatic actuators to change the shape and a thermoset epoxy to hold the shape in place. The next one is the idea of a morphing skin. This activating skin can wrap around, this is just wrapped around clay. And it can change its morphology when it encounters an obstacle to get over this obstacle. And so it's a different approach to maybe path planning or obstacle avoidance through morphology. And then this next example is a caterpillar type robot that can inch, but it can also go in this ballistic rolling gait when threatened. It's biologically inspired. And then this next robot has an internal bladder that can inflate for a rolling gait on flat ground and then deflate and adapt a new gait to go uphill. And so these robots are wonderful examples of the current state of the art in shape-changing robots. But what's inhibiting more complex examples of these shape-changing systems? The answer, as you might have guessed, is sensing. The previous approaches to shape estimation generally fall short. So for example, in our field, if you have an elastomer cylinder, maybe with sensors on it that can stretch, and the cylinder deforms, then yeah, you get a sensor value which corresponds to a length change. And so you know your shape was a cylinder, and so you say, hey, this length increased, my cylinder is now a deformed cylinder. So it requires this mechanical model. But soft robots are very difficult to model. And also, what if you wanted this to turn into a quadruped? Maybe you could add a couple more sensors. If you wanted to turn it to a fish, I don't know, put a sensor on the bottom. But what if you didn't know what you wanted it to morph into? What if eventually that's something the robot's figuring out? You don't have these predetermined shapes. Are you covering it in sensors? Hopefully not. That would make it even harder to model, not to mention the error stack-ups makes this a really infeasible method for the future generation of shape-changing robots. And so to achieve this closed loop shape control in soft systems, we need a sensing platform that doesn't depend on these mechanical models, and also, of course, can allow and sense these surface strains. They need to be able to deform to extreme strains. And so this brings me to the work that I'm presenting today, stretchable shape sensing ribbons. And so this is based on a concept that combines orientation and stretch sensing. And so if you have orientations along a surface and you have stretch sensors getting the distance between them, you can accurately reconstruct that shape in free space, let alone on a body. And so this is the platform that I'll be discussing today. We have an orientation sensor breakout board, 6 of them, that are just attached simply with Velcro. And it's on this stretchable sensing ribbon. So there are 6 sensors in between each orientation sensor breakout board. And now let me dive into the stretch sensor just a little bit. This is how it works. It's completely made out of textiles and breathable adhesives. So there are 2 textile electrodes. And then throughout this ribbon, there's a common cotton dielectric. So that's what links it all together and makes it a ribbon. And then, of course, you have the strain limiting pieces of fabric over which we place the orientation sensor breakout boards. And so the sensor works, as you might have guessed, as a stretchable capacitive sensor. It's just a parallel plate capacitor. It's shielded. And all these fabric layers are attached with this breathable adhesive film. And so, of course, you end up with a sensor that has some XY area and a thickness. And so the change in capacitance will increase as you, or decrease, of course, as you change these parameters and stretch the sensor. And that's how the sensor works. And so now we have a system that's capable of capturing stretch shape without a mechanical model. This is just the ribbon in free space. And so you have a couple of orientations along the, just these are two example orientations. Obviously, all of them are measuring their orientation. And then you can stretch it and you get some shifted orientations, but you also get a different sensor measurement between the orientations. And so you're able to reconstruct this initial shape and then the stretch shape. And so this is a fundamental principle. But with this platform that we've made, how do we design and test shapes that represent this future class of morphing robots? The hardware doesn't exist yet. So going back to this illustration, and with some current robots, we have spherical robots that maybe get a little bit longer and go into inchworm robots, and again, can get into these quadruped type shapes. And so maybe these look like this. Maybe they have different number of lobes. If you have a different number, if you have 3 legs, you can add 3 legs. So maybe we just vary radial frequency, amplitude, and scale, because these things will grow, to try and capture this class of robots. And so that's what I did. Shows up, yeah. And so we use this formula that already exists that generates shape by varying amplitude, radial frequency, and scale. And scale in this case correlates to the strain of the sensing system. And so that's what's important to me. So that's the factor that I varied. And so we did this. I just laser cut them out of acrylic. We varied the radial frequency and then amplitude and scale on this axis. So our sensing ribbon at the top row is at 0% strain, at the bottom is at 40% strain. It's a good set of shapes that we can simply wrap our sensing system around to try and estimate it. And so this is kind of our hardware side. Now, how do we reconstruct the shape? Of course, we get a calibration curve for the sensor to get the displacement when the sensors are stretched. And this is very simple, just on an Intron or mechanical testing device. And then so take, for example, we have just this little segment of a curve that has 2 orientations on either end. So maybe it's just one pictured here. And we take these measured orientations, they're quaternions in this case, and we can use just spherical linear interpolation to interpolate between these curves, which is basically, it interpolates from orientation to orientation along a sphere. And so then, of course, knowing the distance between our sensors and then dividing that by the number of interpolated orientations, we can get a good reconstruction of the curve in between orientations. And so that leads us to our results. This system can capture increasing scales with a slight increase in mean average error. It can capture changes in this radial frequency and increasing amplitudes, also with slight increases in error because these curves get sharper and sharper at the corners, which is good to note, until, of course, logically, there are less than 2 orientations per curve on the surface. And so this is just an experimental validation of the Nyquist-Shannon sampling theorem, which says that, if you have a sine wave, you need 2 tangents to reconstruct it. So if you just added 2 orientation sensors to our system, you'd be able to reconstruct these shapes. But this is just like the bare minimum sensors. You can have 3, you can have your radial frequency equal to 3, and that's the design rule. And so this data shows that this is a promising platform for future soft and morphing systems. And so this contributes to this new paradigm from our lab for stretchable surface-based shape sensing, which again takes orientation sensors and highly stretchable sensors to reconstruct shape. And now, I spoiled it a little bit, I'm working on the platform in 2D, so making a 2D shape, 2D sheet that can estimate 3D shape. And so I'm trying to figure out the best algorithms right now to work for dynamic shape sensing, because eventually I want to use this to close the loop on shape in software LUTs in the future. And so that's me. Thank you.